Good morning. People, 10 more minutes or so here. I'll get things started to get set up now. All right, well, if you're waiting around, might as well make sure that you can do these two problems that were the prompts to attempt before class. Of course, you're gonna get points for these, but still a good warm-up.
No, I don't have time to take a shower and stuff, not rush.
Hey, Audrey, we can see you and hear you. You might want to turn off
Yeah,
your
no.
video.
I'm trying to turn it off.
This is a little new for me, too. if you're looking at the thing, you can do that right here on this little, you can mute right there. There you go, disappeared into anonymity. Alrighty, well, it looks like there's about 28 here. If you scroll to the bottom of your screen when you see the share, there's a manage participants button or a participants button on the other thing. And if you click in there, you can raise your hand and I'll be able to see that. But besides that, I'm just gonna kind of go through the lecture and I'll give you guys time to think throughout and then I'll post the video. So let's take a look at these first two problems here. These are both really straightforward chain rule problems that require just a single application of the chain rule. So for problem number 11 here, let's first draw, let's draw these functions out and see what the actual two different functions are. So the inside function, I'm gonna go ahead and write in blue here. That's the polynomial, that's the inside function, and then this thing raised to the 10th power is the outside function. So we can think about the outside function as being like we have whatever's on the inside and we're raising that to the 10th power. So it's the operation that has to do with raising something to the 10th power. And the inside function is the polynomial, 2x cubed plus 5x squared plus 7. So if we think about the derivative of the outside, it's going to be 10 times whatever's inside of that function to the 9th power. And the derivative of the inside function is 6x squared plus 10x. So now we're going to combine these things over here to figure out the derivative of this composite function, so a function inside of the other function. So when we're taking this derivative, first we're going to do the derivative. I don't know why I keep writing 9 there. We're going to do the derivative of the outside function first, and we're going to leave the inside the same, and then we're going to multiply by the derivative of that inside function. And that's basically all we're going to do for this whole lesson, but we're going to do it in a lot of different ways and make sure we know what's going on, because this is probably the most complicated of the derivative rules, and this is the last of the derivative rules. So let's see if we can do that now for this cosine function. Leave that one up there on the screen right there. Okay, so on this cosine function, we can see that the cosine is the outside function. So it's like cosine of something else. That's the outside function. So when we take the derivative, we can take the derivative of cosine, and the derivative of cosine, let's do that in blue like I was, the derivative of cosine is negative sine. So we take the derivative of g. First thing we're going to do is take that derivative of cosine. So we have the negative sine, and then we leave the inside exactly the same. So that's our 2t cubed plus 5t squared. And then we multiply by the derivative of that inside function, which is 6t squared plus 10t. And yeah, so that's how you would have done those two problems that you could have done after watching the lecture videos. So we'll keep on going throughout this, and I'll give you a little bit more time to think about some of these other problems as we go through them. So we're not adding any more concepts here, so let's take a second, and why don't you guys try to work through example 13 for just 1 second here. Something that you're going to want to pay attention to with this one is that if we're going to do the cube root of x, we can rewrite that as x to the 1/3 power. That'll make it a lot easier to take this derivative. This is actually our outside function. Now that you're thinking through this a little bit, it's also worthwhile to actually write the chain rule out. So let me move that down just a little bit. Oops. So the chain rule says that when we're taking the derivative of a function inside of another function, we take the derivative of the outside function first, leave that inside function the same, and then multiply by the derivative of the outside function. So when I keep saying outside function, I'm talking about that f function on the outside. The inside function for this thing is that 1 plus tangent of x. And if we're going to take the derivative of that, we get 0 plus secant squared of x. So now let's combine these things to find our full derivative. So I'm going to start, I'm just going to rewrite g of x. I'm not taking any derivatives now. I'm just rewriting this using the power function notation. So we want this to be to the 1/3 power because that's going to make our derivative a little bit more straightforward. Now when we go ahead and take the derivative, we're going to take the derivative by starting with the outside 1/3 power operator. That's that cube root. So when we subtract 1 from 1/3, we get a negative 2/3. We're going to leave the inside exactly the same. And then let's get this out of our way just a little bit. And then we're going to multiply by the derivative of that inside function, which is secant squared of x. It's 0 plus secant squared of x, but we don't need to write that 0 in there. Alrighty. Now let's take a look at part B here. So 4 secant of x over 8. So this one's a little bit weird because that x over 8 is the inside function, even though It's just a coefficient in there. It's no different than if it was like 3x. So let's pick this apart and see what our different functions are. So our outside function is 4 secant of something. In this case, it's x over 8. And the inside function is the x over 8. Okay. And so if we think of the derivatives of each of these functions, the derivative of 4 secant of something is 4 secant of that thing tangent of that thing. And the derivative of x over 8, some people want to use the quotient rule on these kinds of things. You don't really need to use a quotient rule because we can think about this as just being 1/8 x instead of x divided by 8. And when we take the derivative of 1/8 x, the derivative is just 1/8 because that's a linear function. Okay, so now let's combine those to write our derivative here. Give you a second to think about that. I'm going to leave that up right there and see if you can get that derivative on your own. Oh man, look at that. We're up to 40 people logged in. It's pretty interesting. Kind of neat. Okay, so how are we going to take this derivative? Well, we're going to start by taking the derivative of the 4 secant part. So we have 4 secant of something tangent of something. And our something in this case is x over 8. And then we're going to multiply by the derivative of that inside function, which is 1/8. We can go ahead and simplify this one step. You don't need to do this for quizzes, exams, or web work. We're just going to do it to make it a little bit simpler to see what our final answer was here. So the trickiest thing about this problem is that this like x over 8 thing doubled. Because that is still the inside function, and it's just because secant over here has a really weird derivative where the argument, that's the thing that you're plugging into the function, it gets repeated in the derivative of secant. It's kind of a unique function in that sense. Like most of the time when we take the derivative, we either keep the same number of places where we plug in or we decrease them in the case of polynomials. But for secant, we actually get another place to plug things in, which is kind of weird. It happens also with the quotient rule. All right, so hopefully this is making a little bit of sense. This is very procedural. It's just like 2-3 and 2-4, where 2-3 was power rule, quotient rule, product rule. 2-4 is trig derivatives, and then some of that trig ratio stuff. And then 2-5 is just all of this chain rule stuff. So keep blazing forward here. Now we did a bunch of examples that were really formulaic because they were like we had the formula and it was just a direct application of the chain rule. Now for example 14, we're going to need to use a table with the chain rule. Looks like we have one person. I'm going to go ahead and mute the new joiner just so that they don't accidentally talk here. So I can, okay. Alrighty. So let's go ahead and think about this one a little bit. All right, so we're just going to need to follow the definition of chain rule exactly for these to make sense. So let's work on part A here. This is a direct, we can just like sort of copy the chain rule. So we have f of g of x. And we're trying to find the derivative of this thing And then we're going to evaluate it at x equals 1. So the derivative of f of g of x is f prime of g of x times g prime of x. But then we want to plug a 1 in for each one of those x's because we're evaluating it at x equals 1. So we get f prime of g of 1 times g prime of 1. And we're going to be able to just evaluate those based on the table. So g of 1, so I look at g here and look at the 1 value is 3. So we're evaluating that g of 1 first before we find the derivative. And then g prime of 1 is 0. It's actually going to zero out the whole equation. Oh, whoops, we're not going to write g prime there anymore. We evaluated g prime. That is 0. And then f prime of 3 is 11. Okay, so we have 11 times 0, and that's just 0. And that's our answer for part A. And for part B, we're just going to reverse the order here. So we're going to take the derivative of g of f of x. Lots of parentheses going on there. And when we do that, we're going to take the derivative of the outside first, leave the inside function, multiply by the derivative of the inside function. And I'm going to go ahead and grab this whole line here and move it down so we don't run into our last work. Oops, right there. Slide that down a little bit. Okay, so now we're going to plug, in this case, we're plugging in 1s here and here. And I want you guys to go ahead and figure out those values really quickly. So I think when you do this, you should get a -6. Okay, how do we do that? So we have g prime, and now we're doing f of 1 on the inside right here. So when we do f of 1, we get a value of 2. And then when we plug in f prime of 1, we get a value of 3. Oh, I did that wrong when I was thinking. Okay, so f of 1 is 2. Oh, it's not a -2. So I got to write my work. Okay, now we look at g prime of 2, and g prime of 2 is actually 6. And so we should get an 18 there for our final answer. And now c is a little bit different, but it's the same idea. We're just taking the derivative of f inside of f. So it's going to be f prime of f of x times f prime of x, where the second f prime is the derivative of that inside f. And then again, well, no, this one's a little bit different. Now we're evaluating it at 2. So we're going to leave the f prime. We're going to take care of that in just a second. When we find f of 2 is 1. And then f prime of 2 is -5. And then f prime of 1 is 3. So we have 3 times -5 is, I'm running into my other things, is -15 in there. And that's going to be our final answer for that one. So that's almost the same thing, just using tables instead of the functions, like the algebraic functions to do chain rule derivatives. just following the form of the chain rule throughout the problem. Alrighty. Now we're going to do something just slightly different, not too different though. So we've done algebraic functions, like the formula, and we've done a table. So now we'll want to do a graph. This is going to be a little bit weird because we're going to need to calculate the derivative based on the function of f. So this function over here, this is the line that gives us f. So in this thing, when we need to find f prime, we're going to need to manually estimate the slope. Alrighty, so let's take a look at number 1 here. We're trying to find the derivative of f of x at x equals 2. So again, we're going to just apply the chain rule right away. So we're going to take the derivative of f whenever and then we're going to leave the f on the inside. Then we're going to multiply by the derivative of f. That seems kind of weird. There's a lot of f's going on there, but just follow them one little step at a time. So first of all, I'm taking the derivative of this outside f right there, and then we're leaving the inside f the same until we take the derivative in the next step. And then we're going to go ahead and we're going to be plugging in a 2 into here. So we're going to be finding f prime of f of 2 times f prime of 2. And calculating f of 2 is easy. That is just that y value right there. So we're going to be finding f prime of 1 and multiplying that by f prime of 2 right there. So how are we going to do this? This is actually an estimation problem. We're not going to be able to calculate this exactly. So given a graph, what is f prime on the graph? It's the slope of the tangent line, right? So it's a little hard for me to draw tangent lines on the tablet. Let me see if I can get a little bit better line here. So we want to find the slope of that line. So the green one here. Okay. That green one is going to be the derivative at 1. And then we also want to find the slope at 2. And that slope is going to be f prime of 2. Now they look like they're pretty similar, and that's just because this graph happens to be such that they're pretty close. It wouldn't necessarily have to be the case. And I'm going to treat these axes, they're not labeled, so we're kind of doing a lot of hand waving here. I'm going to treat this as being a 1-by-1 graph. And then how am I going to estimate this slope? Well, I can just drop some points on this line. So we can put a point there and a point there. This is like the point 1, maybe 2.3. And this is the point up here, like -1 and 1, 2, 3, 4.4 maybe. And now I can find the slope between those 2 points. We can see that goes down 2.1 and over 2. So our slope there is 2.1 over 2. And again, I got that by doing 4.4 minus 2.3 over -1. Oh, that should be a negative there, -1 minus 1. And when I compute that, I get that -2.1 over 2. That's an estimate. You could have gotten a different number. And then we need to multiply. We're going to do the exact same thing on this next, on the red little tangent line here. Notice though that this goes down 1 and over 1. So I'm just going to call that a -1 slope right there. They're both really close to -1. And then when I multiply those two things together, I get, we can do like, that's a 1.05 is the number that I get, or I could have just done 2.1 over 2. That's also an okay answer there. It's just an estimate. The idea here is how do you like trace that estimate, and how do you think about the derivatives using the graph. For problem number 2, our work is going to be a little bit easier because the inside function is defined. The inside function in this case is the x squared function. So when we take the derivative of that, we're going to take the derivative of the outside function. We're going to leave x squared in there, and then we're going to multiply by 2x, because 2x is the derivative of x squared. And then we're going to go ahead and plug in. We're calculating at x equals 2. So we're going to go ahead and plug in 2 into there. Oops, that's a times, not an equals. Okay, so we're finding f prime of 4, and then we're going to multiply that thing by 4 when I do some of that simplification. Okay. So I need to now calculate f prime of 4. If I look back up at this graph, I need to go over to x equals 4. I'm trying to find the tangent line there. We're trying to find the slope of this tangent line. Looks like we go over 1 and up about 1.4 maybe. If I'm thinking about using the point here for 2 and the point there 5, 3.4. And so my slope there is 1.4. Multiplying that by 4, and that gives us 4 and 16 is 5.6 would be our slope. Oops, don't want to do that. 5.6 would be our slope for that one. Alrighty, so that's, now we've looked at a table, we've looked at a graph, and we've looked at some formulas. So now we're going to look at some more complicated problems, algebraically. Alrighty, so this problem we're trying to find the derivative of cosine to the 6th of x. The first thing that we need to address is, what does cosine to the 6th mean? Well, cosine to the 6th of x is shorthand for the cosine of x raised to the 6th power. Okay, we're going to do a quick little side note here. This isn't just a notational thing. So if we write the sine of x squared, this is meant to mean the sine of x. So you're finding the sine of x first. No, I lied. Ignore me. This is like finding the sine of x squared, where you're doing x squared first, and then you're taking the sine after you square the x. Versus when we do sine squared of x, that means that you're taking the sine of x first, and then you're squaring on the outside, and that just affects the order of operations, which affects our derivative. So it's important that we remember that cosine to the 6th of x means cosine of x inside raised to the 6th on the outside. So when we do the derivative, so our outside function is that 6th power. So we're going to have 6, whatever's on the inside raised to the 5th power. What was on the inside was that cosine of x function. And then we're going to multiply by the derivative of cosine, which is negative sine of x. And this answer is completely fine. But we could think about this as cosine 6, cosine to the 5th of x times negative sine of x, if we were going to convert back to that notation that we started with. Both of those are acceptable. This is just different ways to write the same problem using different notation. Right. Now let's use this information. You're going to have to think about your unit circle. Let's find the equation of the tangent line at x equals pi over 6. That's a nasty one. So equation of the tangent line, immediately I'm thinking y minus y1 equals m x minus x1. And I know that my x1 is pi over 6. How do I find my y? I'm just going to plug in pi over 6 into my original function. So we're going to do the cosine of pi over 6 raised to the 6th power. Again, looking at our original function there to get our y value. Cosine of pi over 6 is root 3 over 2. And then we're going to raise that to the 6th power. Ugh. I'm just going to leave that there. Root 3 over 2 raised to the 6th power, because I don't want to, that's some number. If we want to get really fancy, this is 27 over 2, 4, 8, 16, 32, 64. And that's because this top ends up being 3 cubed and the bottom ends up being 2 to the 6th. Ends up being 3 cubed because the 6 is the 6 in that square root is a 1/2 power, and 6 and 1/2 are 3. So we get 3 cubed and 2 to the 6th by using some of our exponent rules. We're not gonna, I don't really care about getting that simplified. Now the main issue that we have here is figuring out what m is. We're gonna use this to calculate our m. Okay, this is f prime of x. So to calculate f prime of pi over 6, we're just going to plug pi over 6 into that thing. So we get, let's do that, let's separate this so we know this is for our next problem here. So we have 6 cosine of pi over 6 raised to the 5th power times negative sine of pi over 6. Alrighty, so that's what we're plugging into the old derivative. Now we're going to have to simplify that a little bit. And so we get 6 cosine, oh no, we're going to evaluate the cosine. Root 3 over 2 to the 5th power times negative 1/2. Sine of pi over 6 is 1/2, but we have that negative that we're carrying along with it. So this gives us negative 6 root 3 to the 5th power divided by 2 to the 6th, because we have a, this here is that we have a over 2 to the 5th times 1 over 2, so that ends up giving us a 2 to the 6th. That's all kinds of crazy nasty stuff. Let's just drop this thing right in there. That's the slope of our tangent line. And then if you need to put this into your web work as a y equals, all you need to do is add that root 3 over 2 to the 6th power to the other side. So this is going to be nasty, but what we're going to get is we're going to get 6 over root 3 over 2 to the 5th power times negative 1/2. That was our original m. And then this is going to be multiplied by our x part, which is x minus pi over 6. And then we're going to add over our y part, which was root 3 over 2 to the 6th power. Root 3 over 2 to the 6th power. You might be asking, why are we doing such a crazy derivative problem? The reason why is because this is just pushing your computational fluency a little bit. We're going to make the numbers a little bit more crazy so that numbers that are less crazy seem a little bit easier. But that's how you're going to do that. That is number, it's labeled up here, that's number 5 in the 2.5 web work. Alrighty, this is number 6 in the 2.5 web work here. I guess I can scroll up there and let you guys take some of that in. I want you guys to work on example 17 here really quickly. Think about what you need to do. Separate your functions a little bit. If you guys want to use the chat box, you can ask some questions via chat. I can also take questions via voice recording, but that seems a little bit daunting with 50 participants logged into this thing. So whatever you guys want to do. I'll give you just a couple of minutes to work through example 17 here. Oh, thanks for the question, Perry. All right, so the question is, for part A of this problem, what if it were x squared? You're saying x squared on the inside? Is that what you're thinking? Okay, so let's take a look at that. We're gonna just pull this over here. So we have a y equals cosine to the 6th, and you're saying if that's an x squared in there, just like that? Great. Okay, so this is actually going to be a triple chain rule, which is a really, really great question. So let's think about our outside function here. Our very outside function is the 6th power. Our middle function is the cosine function. And then our inside function is that x squared. I guess we can just write it as the x squared. That's all the way on the inside. So I could rewrite this to make that a little bit more obvious. So I can do, we have our thing to the 6th power, and then we have cosine one step inside of that, and we have x squared one step inside of that. Okay. So then when we take the derivative of this, first we're going to take the derivative of the 6th power, which we bring down the 6, lower the power of the 6 to a 5. Then we leave the inside function the same. I'm going to write the stuff that we're leaving the same in gray. Then we need to multiply by the derivative of that middle function, which is negative sine, because the derivative of cosine is negative sine. And then we need to multiply. In this case, we have another multiplication where we're going to multiply by the derivative of the very inside function, which in this case is 2x, rather than just a 1 if it was just x. So it's pretty much the same. We just get that 2x at the end, and then we have these x squareds in the middle that we're carrying throughout. And then Lamar has another question here. When we did that with the graphs and we were estimating, so let me know if you have any questions about this thing. We'll come back to that. When we're estimating the graphs up here, do we need to do an approximation sign? Yeah, we could, since this is all an estimation. These are really always going to be approximations because we're estimating the values on the graph. But we'll never be really picky about whether or not it's estimation or direct calculation. It's always going to be obvious to us if as a grader, because you'll be able to calculate it directly if you're given the function as a formula. But if you're given a graph, it's always going to be an approximation. But yes, we could use squiggle equality signs there. Nice job finding that symbol, by the way. Did that answer both of your questions there? I'm going to scroll back down here so you can take that in a little bit more. Are we good on this? All right. Slide back over here and take a look at this problem again. Hopefully you're still working on that problem. All right, Perry says we're still good. That's good. All right. So I'm going to start. I'm just going to write the answer to this to start, so you can check it, and then we'll go back and do the work. So this should be 3 secant squared of 2 cosine of 5x times -2 sine of 5x times 5. All right. So let's figure out how that made sense. I'm not gonna write out all of the functions. I'm gonna just write them in different colors as we go throughout this. So if I'm looking at this, the first derivative that I'm taking is going to be that outside tangent function. So I'm going to do 3 secant squared of the inside function, 2 cosine of 5x, which is remaining unchanged, and then I'm multiplying that by the derivative of that inside function. Now the derivative of the inside function, so we have a cosine function there. 2 is just a constant. We're just going to bring that along for the ride. And the derivative of cosine is negative sine. And again, we're going to leave that 5x because that's the inside. We're going to leave that the same. And we're going to need to multiply here by the derivative of 5x. And of course, the derivative of 5x is just 5. So now if you combine this and this and this, we get our final answer there. Okay, so that is related to that question you had, Perry, where we have a triple chain rule. In this case, we don't have an x squared, but it is a function within a function where that inside function is just 5x rather than something maybe more interesting like an x squared. And then notice here that it's the 2 is carried and then we have a negative sign, so I simplified that to a -2 down there. You could have collected all of these constants, so we could have maybe collected, we have a 3 and a -2 and a 5, that's a -30. And then we have secant squared, and we can't take this 2 out of here because it's on the inside of secant. And we can't take this 5 out of there because it's on the inside of sine. So that's a little bit more simplified version of that problem. All right, and now we have 2 more web work problems for parts A and B here. So I'll give you just a second to take a look at those. Give you guys another second to ask some questions if you want. I'm gonna zoom out and scroll up just a little bit so you guys can still see that answer there if you're still working on that. I'm gonna have you work on A and B really quickly. These are both just single chain rules. This timing is going pretty well. I think we should finish up here in the next 10 minutes or so. I'll give you guys one bonus problem at the end that combines a lot of different derivative rules into one to try to work through that in a little bit more complicated way. Remember that for this example 18, we're trying to find equations of the tangent line, which is it just contains finding the derivative in it, and then we plug that into the line form. Okay. All right, let's take a look at part A here. You've hopefully thought about that for a second.
Это не для того, чтобы делать лекции.
Oh, we got somebody unmuted there. No worries. Okay. So first of all, we're going to start by finding the derivative here. And I'm not going to write the steps. Let's just see that this is 10, 1 plus 2x to the 9th power times 2 because that's the derivative of the 1 plus 2x there. Okay, I'm looking for the equation of a tangent line, which tells me right away that I'm trying to do y minus y1 equals m x minus x1, and I need to find the slope in order to get my m. Okay. I'm also going to need to find regular f of 0, because this is going to be my y1 value. When I'm looking for f of 0, I'm going to get 1 plus 0 to the 10th power. So that's just a 1 in there. So that's my y1 value. So I have that x is 0, y is 1. And now I also need to calculate f prime of 0 using this equation that's going to give me my m. So when I do that, I get 10 times 1 plus 2 times 0 to the 9th times 2, and that just gives me a 10 times 1 times 2, which is a 20. So my m is 20. Calculating the derivative, plugging in the 0. Now I just combine all of these things. I get y minus 1 equals 20, x minus 0. Can simplify that a little bit if I need to get it to a y equals. Y minus 1 equals 20x, or y equals 20x plus 1. And that's what I would plug in for the slope of, or the equation of the tangent line for part A there. Okay. Part B. All right, let's start by finding g of 2, because that's going to be my y1 value. So we have the square root of 1 plus 2 cubed, conveniently chosen numbers. That's 1 plus 8. 1 plus 8 is 9. The square root of 9 is 3. If I'm going to calculate g prime, first let's calculate g prime of x. And to do that, we might want to be thinking about g of x as being 1 plus x cubed to the 1/2 power. So when we take the derivative, we get 1/2, leave the middle, 1 plus x cubed to the negative 1/2 power times, because of chain rule, 3x squared. And you don't ever need to simplify, but since I'm going to need to do this calculation to get the number, I am going to simplify just a little bit. And the main thing that I'm trying to simplify is this part of the expression. This ends up being 1 over 2 square root of 1 plus x cubed. Okay. So the 1/2 is that 1/2. And then I get this, the square root in the denominator, because I have this negative power there. So that moves it to the denominator. And that just makes it a little bit more clean, because then when I'm multiplying that by 3x squared, I have 3x squared over 2 times the square root of 1 plus x cubed. Okay. And so now, if I'm trying to calculate g prime of 2, then I get 3 times 2 squared over 2 times the square root of 1 plus 2 cubed. So I get a 12 there on the top, and I get a 2 times 3 on the bottom, because again, that's the square root of 9. And so I get 12 over 6, which is just an easy 2. So I have my y is 3, my m is 2, and my x is 2. So when I write the equation for my tangent line, I get y minus 3 equals 2 times x minus 2. If I wanted that to be a y equals, I get y equals 2 times x minus 2 plus 3. And that's all I really need to plug into the y equals for web work. Okay. Then I'll let you work on part C here. This is the last problem on the notes, but after we do that, I'll have one more bonus example for you that will help you feel good about this, because we'll tie together the chain rule, product rule, and quotient rule all into one problem and see if you can follow along, and that'll be a good check that you know what you're doing. Why don't we do part C first, and I'll leave you guys another chance to ask some questions if you have questions about part A or part B. So I'll give you just 3 or 4 minutes here to work on part C. Alrighty, so this one's pretty nice. We already have our x and our y given to us, so we don't need to do that extra step of calculating for x. We just need to find the derivative. So the derivative here, hopefully you're a little more comfortable with this by now, is cosine of x plus, okay, we have 2 sine of x times cosine of x there. All right, so the 2 sine of x, this is the derivative, this sine of x, maybe we'll do that sine of x right there in gray. So I'm not changing that. So the 2 comes from the derivative of the squared. We leave sine of x, cosine of x is the derivative of sine. So now when we calculate the derivative at 0, because of x equals 0 right there, so we get cosine of 0 plus 2 sine of 0 times cosine of 0. So we got to think about our exact values of our trig functions. 1 plus 2 times 0 times 1 just gives us a 1. That is our m value. So then we have y minus 0 equals 1, x minus 0, or just y equals x. It's just the unit slope line. Alrighty, that's all of the fresh, or the problems on the notes, but I'm going to give you one more problem now. And I'll show you how we can construct this problem actually, so you can write your own. And this is actually an interesting way to do some quizzing if you are working with somebody. So, well, what I want to do is let's come up with 3 functions here. We have f of x is, how about x squared plus 5 of x. And then let's take g of x, and how about we make this one square root of x, and then let's do h of x, and we'll say that that is sine of x. Okay. And so let's combine these in 2 different ways to illustrate how you put together these functions in interesting ways. So first of all, for the first problem, let's do, how about f of g of x times h of x. Okay, and let's find the derivative of that thing. So first of all, let's figure out what this, oh, that's actually going to be hard. Let's not do f, because that's going to be weird. Okay, let's do g of f of x times h of x. Okay, let me show you real quickly why f of g of x times h of x would have been a weird problem, because we would have been plugging in g times h into both of those x's. So it would have been square root of x sine of x squared plus 5 times, that 5 is part of the function that I wanted to be read, 5 times square root of x sine of x. And that derivative is really nasty, so we're not going to do that one. But if we do g on the outside, okay, so what we're going to do is we're going to take our f and our h and we're going to put them inside of that square root. So we have a square root function there, and then we're going to put f, and we're going to put h inside of that square root function, sine of x. Okay, now let's try to take the derivative of this thing. Okay, so we're going to try to take the derivative. And so when we do that, we're going to get g prime of f of x, h of x. And then we're going to, when we multiply by the derivative of the inside, you see what's tricky about the derivative of the inside here? The derivative of the inside is actually going to be a product rule. Okay, so let's see how that works out with the actual functions that we're using. So first of all, we're going to take the derivative of the outside there. So that's going to be 1/2 thing to the negative 1/2 power, because we're taking the derivative of that square root function. So we're going to leave x squared plus 5x times the sine of x on the inside. And now we need to multiply by the derivative of that product function. When we take the derivative of that product function, what are we going to need to do? We're going to need to use product rule. So we need to do 2x plus 5 times sine of x plus x squared plus 5x times cosine of x, right? Because we need to, if you're thinking about this as like a u v, then we need to do u prime v plus u v prime. And so where this comes in then is, so now over here, we just have this 2x plus 5 times the sine of x plus x squared plus 5x times the cosine of x. And that whole thing needs to be in parentheses because that whole thing is being multiplied by the original function. Okay, so that's how you would do like product rule inside of a chain rule. And this is the last example I'll show you here. Let's do that exact same idea, but let's switch it around a little bit. Let's do h of f of x over g of x. So when you're looking at this, you can say, okay, well, h is the outside function, then there's something happening on the inside. So we're probably going to use chain rule, that's right. And then when we take the derivative of the inside, now instead of product rule, we're going to need to use quotient rule. Okay, so let's look back at our functions and figure out what we're doing here. Okay, so we're going to be doing the sine, because that's h over here. And then we're taking the sine of f of x is x squared plus 5x, and g of x is the square root of x. So we're going to be trying to take the derivative of that crazy nested function there, a function inside of another function. I want you to try it really quickly for just 2 or 3 minutes, and I'll show you that last example, and then I'll be done doing examples, and I can just answer a few extra questions if anybody has extra questions. And then I'm going to email out this recording to people. And I also, now that you're all here, you'll know firsthand, but we're going to extend the web work deadlines until after Friday at the least, so you guys can ask questions during recitation, and you won't have that web work due tonight. That's actually changed already. Alrighty, so we're trying to take the derivative of this whole function. The first derivative that we're taking is that outside function. We're going to leave the inside function, and we're going to need to multiply by the derivative of that inside function. So we have the cosine of x squared plus 5x over square root of x. And now the derivative of the inside here. Okay. I'm going to do the derivative of the top in red and the derivative of the bottom in green when I write those. So the derivative of the top is 2x plus 5. We're going to multiply that by square root of x. And because that's, if we're going to treat this as like our red is our u and green is our v, this is like u prime v. And then we need to keep u the same, so x squared plus 5x. And we need to multiply by the derivative of v, which is 1/2 x to the negative 1/2. Remember, for your own fluency, that's 1/2 square root of x if we wanted to write it that way. And then we want that bottom part of the function to be squared. And then that is our complete derivative. We could do some simplification if we wanted, but the main idea here is that you're using a chain rule first, and then you're using a quotient rule inside of the chain rule. That got us to 11. We did it. I was a little bit nervous about doing this webcast, but that worked pretty well. So now I can answer some questions. If anybody has questions, you can log out and enjoy the rest of your snow day if you want. But I'll hang around for a few minutes and answer some questions. If you guys want to ask audio questions, I can do that. You can just keep typing questions, or you can go ahead and log out there. All right, I got 2 other questions coming in. Will we still have the quiz on Friday? Yes, but I'm going to switch it to a group quiz. So it'll be the standard quiz. I'm not going to rewrite the quiz, but we'll just take it as a group because I don't want it to hurt your grade. But I still do want to like stay on our schedule. So we'll just do a group quiz on Friday, treat it as kind of a study day. And I'm glad that you guys enjoyed the video lecture. I'm glad that worked out for everyone. Yep, we want to scroll up to example 5.13. Let's go ahead and do that. 5.13 is right there. Okay, and what part of it do you want? And remember, these are available, these lecture videos are available on the main lecture video, or the main OneDrive thing that is always available to you guys on the course website if you want to access it that way. I can scroll around. Let me know if you want part B instead of part A here. Great question about in groups. Yeah, we'll have the recitation leaders. You'll just we'll have you guys work in small groups of 3 or 4 just based on who's around you. And the goal of that quiz will be more of a learning attendance grade. We're not going to try to make you guys have a high stakes quiz here this week. The web work currently is going to be due on Friday, so that you can work with that in your recitation on Friday. And I'll hold some extra office hours on Friday once I get my schedule straightened out, depending on whether or not we have school tomorrow. So right now, the web day, I already updated it. The due dates are set to Friday. If you guys are still a little bit uneasy about the chain rule stuff, you might try problem number 7 in the web work. I can actually post that on here if you want to work through that together. It's a little bit of a tricky one. That is a quotient rule outside of a chain rule. I'll go pull that off of my web work set real quick here. I'm willing to hang around for another half an hour or so if you just want to work on some web work, and I can answer some questions. But let's take a look at this problem first. So scroll down here to the bottom. This is web work 2.5, number 7. Alrighty, so on here, let's grab a screen clipping real quick. There we go. Okay, so this is a weird function because we have this weird thing on the top. That's a chain rule, right? Because we have like sine of x to the -9, so that's 2 functions. But then we have this division, so there's going to be a quotient rule involved, and the main trick here is like figuring out which rule comes first. And it kind of takes requiring like just looking at how that looks and seeing like what's the overall structure. Like, and you can see that like the main thing that's happening is this division problem, and then just the numerator has the crazy stuff in that. So that's why the chain rule is going to be inside of the quotient rule rather than the other way around. So if we're just taking a look at this structure before we even do any derivative stuff, we're going to have the top function here, 5 sine of x to the -9th power. We're going to take that thing, we're going to be finding the derivative of that and multiplying it by x. And then we're going to subtract that top thing, 5 sine of x to the -9th power. And we're going to be multiplying that by the derivative of x. So this is our u prime v minus uv prime. And we're dividing this whole thing by x squared. Okay. So now let's just work with this u prime. I'm going to do that in red. So we get -45 sine of x times cosine, to the -10th power. A lot of people would have put a -8 there. Okay, remember that you're subtracting one from a -9, so it needs to go to a -10. And then we're going to leave our, and then we need to multiply by the cosine of x. And this thing here, that's a chain rule because that comes from the sine. And then we need to multiply this by x. That's this original x. And then we're subtracting. We're keeping our original u, 5 sine of x to the -9th power. And now we need to, I'm going to do v prime here in red. What's the derivative of x? Well, it's just 1. Yeah, great question. How am I multiplying the exponent by the coefficient? I am. So I have that 5, and 5 times -9 right there is at -45. That comes because I'm pulling that -9 down out front. That's exactly right. Yep. And then that -9 goes to a -10 because we're subtracting 1 from it. And then we're dividing this whole thing by x squared. And we can actually just leave it completely like that. But it might be a little bit easier to write it into web work if we just do one step of simplification on our own. So we have negative 45x sine of x. Well, I don't need to move that x over there. That doesn't really help us. Sine of x to the negative 10th. I don't even know if I'm going to be able to simplify this very much. Cosine of x times x minus 5 sine of x to the negative 9th power, all divided by x squared. Yeah, that didn't really simplify it at all, actually. Just got rid of some of the extra writing stuff on there. All right, I'm happy to, so the chain rule being the outside function would look like, yeah, that's exactly right. Yeah, this is a great question, Perry. Okay, so if the chain rule were on the outside, like if this were a different problem, so if the problem were different and we had 5 sine of x over x, that whole thing raised to the negative 9th power, in this case, you're exactly right. If we're taking the derivative of this thing, then we would have done negative 9, kept the inside function, 5 sine of x over x to the negative 10th power, and then we would have done a quotient rule on the inside that would have been 5 cosine of x times x minus 5 sine of x times 1, all divided by x squared. So it would have been the chain rule first and the quotient rule inside of the chain rule, because that fraction's like inside of that negative 9 power. So that negative 9 power is like the full outside function. That's a great question. Yep, just a slightly different positioning of the parentheses, really, and it changes the structure of the problem pretty significantly. That's exactly right. Web work 2.3, number 9. Let's take a look at that one. This is a tricky one. Okay, yep. This is actually one that is on the recitation notes. But I'm going to go ahead and grab this one out of web work really quickly. I'm going to switch to the web work tab here so that we can put this on the web work tab for people. This is 2.3, number 9, and we want to go grab. We can actually do more with that problem now that we know chain rule. There's actually 2 different ways to attack this problem, which is a little weird. Okay, so let's go ahead and drop this in. Right there. Okay. So there's 2 ways to think about this. One way is that we can think about this as being just like it's written, 9x minus 5 to the negative 1 power times x plus 8. And this particular way of doing it, this is a product rule plus a chain rule. And then you can also think about this, and this is a good little preview. This exact problem's on the recitation notes, so you can seem super smart when you're working with your group in recitation, having already worked on this with me. And now we have another one here. We could also just convert this to a fraction by taking that negative 1 power and like interpreting what that means. It means that the 9x minus 5 is just in the denominator, and then this is only a quotient rule. Okay, and that's actually because chain rule, product rule, and quotient rule are all with different exponent tricks. They're actually all the same derivative rule, because this is just a simplification of that f of x plus h minus f of x all over h. These are shortcuts, and the shortcuts are all kind of circular. So let's do the quotient rule first, because that's the most straightforward, I think. So we're going to get 1 times 9x minus 5 minus x plus 8 times 9 all over 9x minus 5 squared. Okay, and we're going to simplify that one step here. 9x minus 5 minus, and then this is 9x plus 72 in there. And that gives us 9x and 9x cancel, minus 5 minus 72. We have a negative 77 over 9x minus 5 squared. Okay, that's one way that we can do it with the quotient rule. Now, how do we do it with the product rule and the chain rule? Okay, so let's just work with the product rule first. And this is like, so we have a u here and a v there, where like the u includes that negative 1 right there. That's all u, and then this is all v over here. Okay, so what we're going to do then is we're going to be taking the derivative of 9x minus 5 to the negative 1 power. We're going to take the derivative of that thing, and we're going to multiply that by x plus 8. And then we're going to add 9x minus 5 to the negative 1 power, and we're going to take the derivative of x plus 8. Okay, oh, that should be y prime, and this should be y prime. Whoops, y prime, y prime. Okay, so now here we have to use a chain rule, just a kind of a simple chain rule. So we're going to get negative 1, 9x minus 5 to the negative 2 power, and now the chain rule is just the times 9. That's the only part of the chain rule there. And then we're going to leave x plus 8 and 9x minus 5 to the negative 1. And then the derivative of x plus 8 is just 1 there. Yep, we can do number 12 after this for sure. And that's the complete thing there. But now let's, can we get these to like kind of look similar? Because this is looking kind of weird here. Let's just play around with this for just 1 second. So this first factor here, this is really negative 9 over 9x minus 5 squared. And that x plus 8 is on the top. So notice, look over here. That's that term. Okay, that is that same term over there. And it's over the same denominator. So we can see that we can start to see these things are close to being equivalent. And then we have a 1 over 9x minus 5. Now, how would we simplify this more? Well, we're going to have to multiply this by 9x minus 5 over 9x minus 5, right? And so then we're going to get a negative 9x, that's me multiplying there, negative 72, me multiplying there, plus 9x minus 5, that's this multiplication, all over 9x minus 5 squared. And now notice we've actually landed on the exact same part of the work. And that's because the quotient rule can be derived from the product rule and the chain rule. When I'm actually like, to be honest, I don't take derivatives very often. It's not part of my daily life. But when if I'm faced with a quotient problem and I do need to find the derivative when I'm doing some other calculations, I almost never use a quotient rule. I almost always use the product and the chain rule instead, just because I don't know, it's a preference thing. There's less writing or something like that. So you don't ever need the quotient rule if you're really comfortable with the product rule and the chain rule. But usually students in Calc 1, me included when I was taking Calc 1, the quotient rule is a little bit easier if you do have a fraction, just to keep everything kind of in order. Alrighty, now we're going to take a look at number 12 on section 2.3 as well. This is a real bugger. Yep. Good, I'm glad that worked for you, Mickey. Okay, let's go ahead and grab problem number 12 really quickly. Give me 2 seconds. Okay, we're gonna flip there and let's go pull up number 12 here. So number 12 is actually it's actually a conceptual problem. The computation is quite easy, but it's really hard to figure out what you need to compute. Okay, so that's what we're going to focus on here. Know that the main idea here is figuring out what we need to compute, and the actual derivative stuff is actually quite easy. Okay, so first things first here. Let me pull up my chat again to make sure where are we at. There's the chat, so we're following it. Okay. So we are trying to figure out the values of A and B such that this line, okay, it's a line with a variable B, is tangent to this curve. Which basically we're trying to figure out, like, how do we make that be the tangent line at x equals 1? So if it is the tangent line, what must be equal? It must be the case that y prime of both of these is equal to each other, right? Because in order to be tangent, they have to have the same slope at that point, x equals 1. So let's start by, let's get this to be y equals negative 6x plus b. And we can see right from here that the slope is negative 6, and we would get that if we took the derivative, and we just get negative 6 as the derivative. So we know that the slope is negative 6, and we know that this happens, this is a linear function, so that's the case everywhere, actually, for the linear function. But we need the same thing to be true for that quadratic function, specifically at x equals 1. How are you going to do that? So we need the slope at x equals 1 to be negative 6. And the only thing that we can change is the a value. So we take a look at y equals ax squared, and you guys might have different variables on that. Might be ax to the 4th or something like that. If we take the derivative of this, we get 2ax, okay? Because a is a constant, which is a little bit weird because it looks like a variable. It's just saying that we're figuring out if we set a equals to 3, then it would be a constant. So really this 2a thing is a constant, because like if we had y equals 3x squared, then y prime would be 6x. That's all I'm saying here. We just need to figure out like what we're trying to figure out is what does that constant need to be so that the slope is negative 6. Okay. Now, if we calculated the slope at x equals 1, we're going to get 2a times 1 because we plug in that 1. So the slope at the point x equals 1 is 2a, whatever a is. And we also know that that slope needs to be negative 6 from that tangent line thing. And so from there, we get that a is negative 3 just by dividing by 2. Okay, so what we know now is that we have y equals negative 3 x squared as that other function. Okay, now that's almost there. So what we just got is we got that the slopes will be the same at x equals 1, but now the tangent line also has to touch that original function. So the tangent line, this is a tangent here. This 6x plus y needs to touch the y equals negative 3x squared right at x equals 1. So we're just going to do a different equality here. So if we calculate y of 1 of this function, we get negative 6 times 1 plus b. So we get negative 6 plus b. That's the y value at x equals 1 for the linear function. And if we calculate y of 1 for a quadratic function, we get negative 3 times 1 squared, which is negative 3. So we need these two y values to be the same. So we have -6 plus b is equal to -3, which means that b is equal to 3. And those are the two values that would make these two functions land right on top of each other. And it's a little bit of a weird way. It's a weirdly constructed problem because it's just supposed to be a little bit more creative, like the last problem in these problem sets are. The main ideas here is that you're supposed to connect the idea of like slope and derivative and tangent line and keep that separate. So up here we were working with derivatives. And down for the second part of the problem where we're calculating b, this stuff down here is y values. So this is keeping separate in your mind like f prime and y prime from f and y. And so that's the whole point of that particular problem. Can do probably one more question here and then let you guys work on some of your web work on your own. The memorized trig derivatives. Well, you can just Google trig derivatives, but I can write them for you really quickly. I'm gonna switch back to the main lecture and I'm gonna go back to the 2.4 notes to just go ahead and write these right at the bottom of this because this is where we're gonna need to know these ones. So the memorized trig derivatives, what are our trig functions? Sine of x, cosine of x. Actually, let's do sine, secant, and tangent. Derivative of sine is cosine. Derivative of secant is secant tangent. And derivative of tangent is secant squared. I know those so fast because I've literally written this like 1,000 times. So you shouldn't know them that quick. You might have to flashcard them. And now let's take the derivative of cosine, cosecant, and cotangent. And all of these derivatives are negative, and all of them are just the co-functions of their original derivative. So instead of secant tangent, it's cosecant cotangent. Instead of secant squared, it's negative cosecant squared. Those are the 6 trig derivatives that you need for that. We didn't get through the rest of, on 2.4, we didn't get through as much of the limit ratio stuff with like the sine of x over x. There's a nice lecture video on the more lecture videos. Let me see if I can get that to you on the course website. I can share that with you really quickly. I can change my sharing. So let's share instead this screen here. And so on this screen, if you go to the useful links, there's more lecture videos right here. And on the more lecture videos, I think it's derivatives. I think it's 2.4 video 2. Yeah, this is a Patrick JMT video that is, it specifically covers, oh, we don't want to see the ad. I am searching YouTube for math help, don't judge me. So this is the limits of trig function. This is a really great 5-minute video about the trig functions. Oh yeah, Patrick JMT is still doing that. Should we know more tricks about like cosine squared and sine squared equaling 1? No, you don't really need to know much more trig beyond this very basic trig stuff the trig derivatives that we're doing in the OneNote here. We're not going to need to do any trig identities or trig transformations. You don't even really need to do that until you're doing trig substitutions in Calc 2. So basically the only trig you're going to need for all of Calc 1 is these 6 trig derivatives, a little bit of that trig limit ratio stuff. That's more just to answer those specific questions on quizzes in the exam. It doesn't really lead anywhere, that limit stuff doesn't. And then you need to know exact values, your unit circle, just to calculate some of those trig values. And I'm glad this was helpful. I've considered doing online office hours, so I might do that going forward because this was pretty easy for me to set up. So maybe we could do some online office hours like the nights that web work is due or something like that. All right, well, it's 11:30, so I'm gonna log off now, and you guys enjoy the rest of your snow day and stay warm. And I'll keep you updated based on we're supposed to hear by noon from the Board of Trustees about whether or not classes are gonna be canceled again tomorrow, and I'll update you guys then. But I'm gonna save this video now and share this with everybody, and you guys have a great day.